So let's say you have your C program, and you're dealing with arrays a lot. You'd like to use arrays. Basically linked my array equal, and you go through your day doing things with your array. Now, for some operations, you want to know how big that array is. So for example, if I just want to loop through the elements and print them, I would probably want to keep a for loop, which I don't, get out of the space that my array is occupying memory, and I don't need to undefined behavior. Sometimes keeping track of the size can be pretty easily. Here, the size is just hard-coded in the array, at least for now. We could also hard-code the size like this. Take the elements here, separate loop, and then we do I+1 just to keep 1 through 5 like we did before, and that would also work very well. Now that's very easy if you have the value hard coded, but sometimes you don't have the value hard coded. When you don't have the value hard coded, this usually means because we are moving the array a lot. So for your C classes, you might have learned that, like basically C knowledge, that arrays decay into pointers. What exactly does this mean? Well, I can use a pointer just to represent my array. I can do something like this. I can declare a pointer. Then I can equate the pointer to my array. And you see that my language server protocol thinks this is completely fine. Everything is going on here, nothing weird. Nothing weird, so apparently the array is an actual pointer. And then we can even, change this thing here to do increments on the pointer. So we dereference the pointer and we increment the pointer with y. And that works because the pointer is pointing to the first element of the array. So basically we are looping the array in the same way that it would be on the array, but this is just more difficult to read, I guess. This is, pointer stuff. See? It's looping through the array. Now, although arrays decay into pointer, it's very important to keep in mind that they are different types. They are different types inside of the language. They aren't exactly pointers. There is this nice Wikipedia page on C types, and the array is a specific type that is defined for every type T. They are not exactly the same as pointers. They're just decaying into pointers in a certain way, just like in languages like Python, which are dynamically typed, or in JavaScript. This happens a lot too, when people like to make memes about how you can, sometimes sort of use a variable as another, and that's sort of what is happening here. And why do I say arrays are not pointers? Because let's say that in this code, that I have this symbol, this symbol my array, that is declared on this specific stack, on this stack frame here, I can reference it. I can do something that I couldn't usually do if I just use a pointer, which is to get the size of this array. And let me show you exactly what I mean. So if I need to get the size of the array, in this case it's pretty easy, it's 5, but let's put a limitation on myself that I can't just type 5 here. Instead I have to take the actual size of the array. Well, that's not hard. I can do int r size equal size of my array divided by size of int. So here the program is obviously taking the entire heap size that the array occupies, getting the heap size of an integer, and obviously since it's an array of integers, it's always going to be a multiple of that, and the multiplier is exactly going to be the number of integers that are currently stored in the array. And if I actually print that, we can recompile our program, and we're gonna see that here in the end it says that the size of the array is 5. It is 5, right? We know that it's 5. So that is working. Now, look what happens if I, instead of using the array, I use the pointer. Because, if they were to be the exactly same object, this should, they should, like, referencing, conceptually, they are referencing the same thing. This, this here should work. And you're gonna see that it won't. The compiler already doesn't, the language server already, it really does not like that I'm doing that. But you see that it returns 2 because like the pointer sort of started as a weird like hexadecimal thing, etc. It's not the point of this, but this is that I really want to emphasize, that array references, when you have then there's this stack frame right here, which is a specific thing. The arrays that are going to be on the heap are always going to be referenced to a pointer, which is exactly the problem that we're going to talk a little bit about right now. But if you do have the name of the array declared on the stack frame, that is not a pointer. It decays to a pointer, but it's not a pointer. It's a different thing conceptually, and this code shows that it's a different thing conceptually. You see that the results we are getting are different results. So now let's go to a different situation. So this, this symbol, my array, does have the information of the size that is occupying on the heap. Great. So let's put ourselves in a situation where we don't have the symbol and we have to use a pointer to reference the array. So to do that, I'll actually create a stack frame. I'll go back to the first way I was fitting it because it was more readable. And then here we'll simply, the pointer is not on the stack frame, the pointer is on the heap. I mean, not exactly, the pointer is on the stack frame of the main function. The only thing in the heap is the actual array right now. And we're going to just, reference with the pointer. Again, the compiler does not complain about this, the array is in the pointer. And now, we're going to talk about how we get the size of this later. Instead, we're going to just check that this, this basic C, this should work. And it does. I didn't put a new line here because I'm inconsistent. So now, let's say, and this happens a lot in actual applications. And this toy example, this isn't what's happening, but it's happening a lot in actual applications. You don't have this magical 5 number here. Then what do? Well, you need to get the size of the array. But what do you do? We're supposing you have no access to this stack frame right now. It's like, it's either generated during runtime, so you really have no access to it, or I don't know, it's somewhere in the code you don't know, you need to like know how to act without it. Do you have any way to put a value here so you don't get undefined behavior, only having the pointer to that array in the current stack frame? The answer is no. The pointer is simply a pointer. The pointer is always just going to be something that is pointing to an address of memory. So if you get yourself in this situation, you're screwed. You can't do much here to really protect yourself against invalid access. The solution has to come a bit before that, of how you structure your arrays. There are 2 solutions to that. One of them is using sentinel values, and one of them, which is the better one for a lot of reasons, and it's the one that when you go to a higher level language, and by higher level language I even mean just C++. C++ is a language that in practice it's very similar to C. They have almost the same features and they are very compatible, but I say C++ is more abstract, not just because of object orientation, which makes it more abstract, but also because even if you're just using C things in it, without using object orientation, it has a lot of libraries and a lot of language features that just can abstract some things for you. It has, the thing that C++ developers like to say so much, which is zero overhead abstraction. The code can run on like a very simple, like very basic C level, but it has a lot of features for you to abstract yourself and make your life easier. And the way that C++ implements things like vectors are to having a struct that kind of stores more sort of, I guess you can call it a type of metadata about the array you are working with. So let's talk about sentinel values. This is bad. Generally don't do this. I'm going to put this here. This is bad. No one does this. But I think it's good to know that it exists because, you know, it's interesting, I guess. So sentinel values are actually what C uses for strings. And I mean, everyone complains about C strings. Who likes them? And the idea of sentinel values is that to store the information about, instead of storing an information only about the size of array, in each array you always store an information about where does it end. So we say in C that a string is null terminated. C uses null terminated strings. What does this mean actually? Well, at rigor, with very rigor, that's just not true. The string isn't terminated with a null value because C doesn't have nullable data types except for pointers. Pointers can be nullable, but except for that, C doesn't have nullable data types. What actually means is this. So in C, each string is indexed to an integer and it's stored in the heap as an integer. But of course, you have infinite integers. Of course, you also don't have that in practice, but you know, conceptually you have infinite integers. Maybe not even conceptually, no, because they're like 64-bit integers. But let's just simplify it. Saying we have infinite integers and we have finite characters. Therefore, there is going to be, you know, a number of integers that are not going to be any character, and you can just choose one of those integers and always format your array of values such that this value that is not indexed by any char, that doesn't index any char, basically just says to your functions, marks that the index is over. So a good example to use this with numbers is to say you know that your numbers, you only make arrays of positive numbers. Okay. Then that's how we would do that. So first we need a sentinel value, and here I'm going to choose -1. So I'll actually use the define thing here. And then I'm going to go here to my array and end it with a sentinel. Then I can actually do this without do this sort of thing that I'm doing here without having a reference to the sentinel. I just do a while loop. It can be a while true. Yeah, C doesn't have true. It's while 1. And at each point in this loop, I'm going to first check whether my pointer is currently pointing to the sentinel. So I dereference pointer. I actually do have to use a for here. Using this while was a bad decision. That's kind of what I want to do. Just having this running, a priori forever and incrementing the y. So the first thing that I want to do in each loop is checking whether the pointer is pointing to the sentinel. So if we dereference the pointer at the current value equal sentinel, then what? Then we're gonna go home. I'm gonna not do anything. Otherwise, we'll print the value and then I'm gonna increment the pointer. And you're going to see that this code is going to work. It's going to be completely fine. You see. Now, the reason people hate Sentinel so much is because they are really unsafe. They make your code extremely bug prone, and these bugs can come in various ways. First of all, every method that does some sort of interaction with this array has to have this actual condition here of checking the Sentinel. No, that just can be really unnecessary. And the other reason is that if someone formats an array without, that's the first reason it's bad. The second reason is that if someone formats this array without the sentinel, the array is just going to break your code immediately when it starts interacting with the functions that assume the sentinel is there. And the third reason it's bad is because obviously having the sentinel restricts your values that you can assume. That's probably the least bad reason, because if you're using the sentinel, you kind of already know, you can assume from your problem domain that value is not going to be relevant. So that's sentinels. Let's talk about structs. So now what I'm going to do is actually interact my array in a way that it's a struct. So let's do that. I'm going to actually create a struct called intArray. What intArray is going to do is that it's going to store a pointer. And it's going to store its size. And the idea here is that now when we want to pass the array around of memory, we don't just pass the pointer that is decayed from the first position of the array. We do that as well, it's inside the struct. But the other thing we do is we also pass, we're passing this entire struct so it has the size of it. So when passing the array around, we pass a pointer to that type of struct. So to create kind of similar code to that, array pointer, and that's the actual pointer we're going to use. Now we'll first initialize a new instance of that struct. Then we are going to use the main pointer to allocate a block of memory for us to do the array things with it. We need to use the standard lib to do malloc. I'm going to actually declare the size before. Then you can use the size of this, just because it's cooler, not for any actual useful reason. And we just allocated memory. Now, all we need to do is use wire or pointer to that. And finally, when we get out, so we are going to get out of this stack frame, we can operate on our array normally. We can, for example, start assigning values to it, and the thing we need to be careful is that now we use the size that is declared on it. So I. So we have to point to pointer. Pointer is a myArray struct, so just do size here. So assign the values we get. So let's go through this. The pointer, we accept the main pointer, and that is itself a pointer, so we have to dereference it. Oh, and we're also, doing allow a y here. And to keep it like the other examples of the y plus 1. That's alright. And here we're going to write another for loop just to print it. And now we can run this thing. And it does the exactly same thing as it always did. So that's kind of the thing I wanted to present in this video, how those kinds of, at a very low level, you can safely pass array around. This helps especially considering how you kind of visualize the applications that are doing vectors, for example, in C++. Why it's an O1 to count the elements on it? Why wouldn't it be like ON operation of looping through trons? Because those informations are coded, and they are coded in it for that reason, that you can't have it without accessing the elements of it. A vector in C also has another thing, which is like the capacity. And the capacity basically would store how much of the heap memory is allocated by it, how many bytes of the heap are occupied by it. And the C++ vector needs that because the C++ is not just any array, it's also a dynamic array, which means that it must move around the heap and allocate new space as it grows. So it needs to have that capacity to know how much more the space it's going to allocate when it moves around. But that's not the thing of this video. The thing of this video is really to understand why informations like length are coded into it and why you should be able to access them straight at the end. All right. So yeah, thanks for watching.